My name is Katie Sugg, and today I'm going to talk about my final project for the summer 2024 REU robotics program. My project was robot leg test bed experiment and strain data collection. I will get into it. So just a quick introduction. My project was based off of the intersection of robotics and neuroscience. As a non-engineer coming into robotics was a little difficult. I noticed that testing robot legs wasn't as easy for non-engineers like me or neuroscientists to easily perform robot leg tests. And so my research focused on going through the requirements of creating a test method or setup for running robot leg experiments. It looked at ways to simplify the complex steps and tried to create an interface that allowed for easy usage for non-engineers. And once I created the system, I had users perform a robot leg stepping scenario where they would go through the steps of creating a footpath to test on the robot leg, calculate the needed kinematics, and stepping the robot leg successfully, and collecting strain data. And then after the scenario was complete, I gave a survey to gauge usability feedback and ways to improve the system. So the first part is the footpath coordinate generation. To quickly generate footpath coordinates, I created a system that would allow the user to quickly and easily click on points. So here it is. You can click on a point and confirm the coordinate. So let me just go ahead and do that. Three points will do. Confirm, and then right here, create the footpath. So this is the footpath created in 3D space, so you can look at it and see if you like it. And if you do, you can save the coordinates. And if you go back to the code, you can see that it says coordinates saved. Of course, if you don't like your footpath, you can clear the points and start over again. Okay, moving on. So to check the footpaths to make sure that they were within the robot leg's range of movement, I made this footpath checker, which uses forward kinematics and different combinations of joint angles to create a point cloud to visualize the leg's range of movement. So around this point cloud, we created a convex hull, which is a polygon. And then once you created the point cloud, the convex hull, as you can see right here without the point cloud, you can test to see, is a footpath coordinate inside this hull or outside? And so that gives you very good information about the footpath you've created. Moving on to the kinematics. So I just mentioned the forward kinematics. To check the joint angles produced by inverse kinematics, we plug those joint angles back into the forward kinematics and compare the output to the original footpath. So this footpath is supposed to look similar to the original footpath that you created. You also just want to look at it to make sure there are no points just in random spots as well. Moving on to inverse kinematics. To calculate the joint angles for a given set of coordinates, the inverse kinematics iteratively adjust the angle to minimize the difference between the desired footpath coordinates and the coordinates calculated by forward kinematics. This was done by using an optimization algorithm. And as you can see from this graph, so this is the change in angles over the footpath coordinates of the 3 servo motors, and the white region represents the swing phase of the leg, and the shaded blue region represents the stance phase. Moving on to the robot leg test setup. So this is the physical robot leg, some of the hardware components. They consist of 3 Dynamixel MX28 AT servos. So right here is the first servo, the second servo, and then the third servo. These servos communicated with the computer using a U2D2 communication converter, and then the robot leg is modeled after the middle leg of a stick insect. Also, these right here are strain gauges, and I will talk about them later. So some of the software components, I used the Python Dynamixel SDK library to communicate with the servos. The group sync functionality is what allowed us to read and write the joint angle information. And I created a Python virtual environment to run all these files. So this is just a SolidWorks design of the leg, and I will play a little video of the leg stepping. Okay, and then going back to the presentation. The wires that you saw on the robot leg were for the strain data collection. So these wires specifically are strain gauges, and they have electrical resistance properties that change in the amount of proportion to the strain applied. So we wanted to get this data to see how forces applied were working on the leg. They were attached, and as the robot leg stepped, a operational amplification board detects the strain and sends it to an Arduino board to be collected. So the results and future work. For the robot leg stepping scenario, every participant was able to successfully create coordinates, calculate kinematics, step the robot leg, and collect the strain for it. They were able to perform all these steps with minimal help. You can see at the very end, maybe someone needed a little bit of help. And asking about the instructions, how clear were they? They were very clear to slightly clear. And then for future improvement of the testing system, the usability feedback that I got would be streamlining more of the coding environment setup and implementing the usability feedback for the footpath generator interface. And then these are my references, and the funding is supported by the National Science Foundation. And then these are QR codes for the code repository and the robot leg demo video that I showed you. Thank you.